How's it hanging, everybody? I was gonna show you something cool I did. I've been wanting to do this for a while, and I found a very powerful tool. And what it what it allows you to do is it allows you to plot graphs of multiple functions at a time, and it's a very powerful thing actually. So check this out. So what we'll do is this is all in a transistor context. So this equation right here is the equation for collector current. As the base emitter voltage changes, it relates those two things together. So with a transistor, your IV characteristic, which is actually the kind of the same thing, is it's exponential. It's not linear. So check this out. So draw this. Kind of looks like it's a square right here, but when you get up close, you can see that it's not Jesus. Never can just zoom in easily. So this is what you got here. Um, so what this equation says is IS here is something called reverse saturation current, and it's essentially how much current will flow through the PN junction when it's reverse biased. So it's a very, very, very small number. It's usually in the nano or microamps, and with small transistors, seems like it can even be in the femtoamps, which is, one order of magnitude below pico. So then you multiply that by E, which is Euler's number. That's a number that pops up a lot in calculus. The curious thing about Euler's number is it is its own derivative, which gives it some very special properties and allows it to be used for certain things. Um, There's a cool video from Veritasium on Euler's number if you're curious about it. It's a lot deeper than what I just told you, but anyway, so X is going to be VBE in this equation. So that is the voltage from the collector, or from the base to the emitter, I'm sorry. And then VT is something called thermal voltage, and it's generally about 26 millivolts if the PN junction is at room temperature. So that's the actual temperature of the transistor device. We're very close to it. So VT is equal to KT over Q. And the reason that I created this variable for it is I wanted to be able to slide the temperature around and see what effect that has on VT. Um, and then K is something called Boltzmann's constant. Now, I don't know a whole lot about that, but I was able to just look it up. It's equal to this. And then you have Q. So Q is something called the elementary charge of an electron, and it's equal to this number. Both of these numbers are extremely small. Um, and then you take that and minus it by 1. So what we're doing is we're iterating over x here. So as VBE grows, going to describe our collector current. So it's going to exponentially rise when we hit about zero point 0.7. Um, this right here is DIB. So this is the change. This is the derivative of, actually, I need to change this to IC. This is the derivative of electric or collector current whenever VBE is changing. So now I've got to go to all these places. Actually, maybe just here. Here. Does it appear anywhere else? I don't think so. I think we're good again. Um, so yeah, these are just constants that are being used here. And then what's happening here is this is your derivative of collector current. So couldn't figure out how to get derivatives to work. They use like I think Leibniz I can't even talk. Notation on it, and it's a tongue twister actually. I don't think I'm Leibniz notation. There we go. So what I did here to create my own derivative approximation is I just took this equation and I subtracted it by change the same equation, but you change VBE by a very, very small amount. You take that difference and you divide it by that small amount, and you get a derivative from doing that. So, VBE, this is your total base voltage. So this is the actual base voltage that you would see if you looked at it with an oscilloscope. That is comprised of two parts. It's comprised of V capital B, which is DC. So this is a static voltage down here. So right now I have it set to zero point 0.7. So it's zero point 0.7 volts DC. And then VSS is voltage small signal, where I just put in a sine function down here that'll be a very, very small value. So 200 millivolts here. And that will add and subtract from VBE. GM here is it's basically it draws the derivative. So this is pretty cool. Check this out. So you take it. So we're drawing the derivative at zero point 0.7 volts. But what we can also do is we can change VBE, raise it, and we end up with a new. So this tangent line that gets created off of this, it's known as transconductance or GM. And so this draws that line for you. Now I had to do some things to this to get it to actually draw the line in place. So this is not actually usable as a GM value for any of the other calculations we're doing. Um, let's see here. TJ is the temperature of the PN junction in Celsius. So 25 Celsius is 77 degrees Fahrenheit. So Uh, it's interesting what happens if we change this as well. Look what happens to our profile. As you can see, as the temperature of that junction goes up, it will start to conduct more and more. Um, all right, we'll turn it back down to 25. That's considered room temperature in most data sheets. So, um, IC is our small signal, or our total collector current, and wonder what it looks like. Yeah. So actually, I'm just using this in other parts of the equations. So let's see. Here's something cool we can do. So let's plot this. Actually, which one was it? Yeah, there we go. So we can plot this, and now we can look. We can change our small signal voltage down here. Let's make it larger. Let's make it 0.3, 0.5, 9. And as you can see, we're going to reach cutoff here. Because what we need to do is we can apply. What I want to do is I want to see this voltage sweep up and down the IV characteristic. I wonder if there's a way that we can do that. I think if we plot this one, oh, it's a constant. No, there we go. Okay. So this is it sliding up and down. So what we obviously need to reduce the amplitude a ton. 900 millivolts would be a huge signal for the base of a transistor like this. So let's start there. That looks pretty good. So you can see we're barely tickling it right now. You know, the transistor is not coming on very far. Um, but if we raise VBE, if we change the bias, the DC bias point, you can see that we start to get closer and closer to amplifying the signal. We can almost reach it. That's really not reasonable. The transistor would be burning up if you did this, but um, let's see what we can do. So zero point 0.7 is generally what you would want to aim for. Um, we're still at room temperature. So let's see what happens if we pulled the transistor down. It would conduct less. If we heated it up, it would conduct more. But you don't want to run a transistor hot, they won't last. You can't even get it hot enough, even at 150 degrees Celsius. It's like 300 degrees. They're not, it's still not. I'm not sure how accurate this model really is. So don't, I just kind of made up some values that were approximations to see. It's really about the relationships between stuff that I care about more so than. Okay, so what happens if we give more signal? Hmm, can't give a ton of signal. Like, we're already. Hmm, that's not even real. Yeah, this is realistic. Um, so we would have about 90 milliamps, a little bit over. What happens if we do the frequency differently? Um, hmm. The other thing that happens, so this is also your input impedance. So this is a beta, that's 300 over IC. That's beta divided by GM. And it's actually pretty reasonable for like the base of a common emitter amplifier usually, like a small signal one. Done a few of those calculations, but maybe it sounds reasonable. There's VSS. It's very small, but it is a sound wave. Okay, let's take this GM out. It's distracting me. Wonder what happens if we mess with IS here. So there's a constant that can actually go before this that you multiply by that kind of accounts for different manufacturing things and stuff. Hmm. Yeah, you can see this sometimes in amplifiers when you're designing them. They hit cutoff. Mm. So, what if we could put an RC in here? So R collector. Here's how you do sub. R collector equals 1,000 ohms. We'll see. Um, well, we can do VC. Let's do lowercase because it's going to be total equals I sub lowercase c divided by, or no, times RC. Ohm's law, you dummy. Capital. Okay, so that would be our collector voltage if we had a 1K. Yeah, that doesn't surprise me. Nothing. Jeez, like how tall is it? Yeah. That's got to be like milliamps or something. Or maybe I'm just dumb. Like maybe I don't know anything. But that's like a fool's errand, it looks like. So Dick. Um hmm, let's just go home. Change our input signal again. What, four 400 millivolts. And make sure, yeah, 26. Okay. What is wrong with EG now? Oh, I need to undo shit. Okay. Go home again. Hmm. See, I just don't think I don't understand why that graph is like 100. Uh, hmm. I mean, this is for small signal only. I mean, what do you do? Hmm. Oh, I mean, that's like 100 amps, you know? Is that amps? Is that milliamps? Like, what is it? It's got to be milliamps, right? I don't see anything that's making it milliamps. Let's see. It is 68. That's DC though. AC is going up into the hundreds. So, what's the deal, dude? Am I using the wrong equations like to begin with? You let me know in the comments, but let's burn her up, boys. 24. This EG number is another thing I'm skeptical of because, see, like a chat GPT told me that 5 times 10 to the negative 14 was a common value for like a 2N3904. And so that's like pretty close. I mean, it's a very finicky thing finding this. I went 48, 49, all the way. What happens like when the temperature of that p-n junction increases? So when this number increases, so that's Kelvin here. It's the absolute temperature is what they're using in these. So you got 273 because that's what 0 degrees Celsius is in Kelvin plus the temperature in Celsius. Normally the room temperature is around 300 Kelvin or so. Um, so that is rough because like I also asked ChatGPT a number for this, and it said like 1.12 electron volts, and that's not even close. I mean, this number is freaking tiny. Um, so I don't get it. Let's actually ask. Okay. Um, hmm. What's a typical value? Energy gap. Oh my God, no. Didn't mean to do that. But yeah, see, it says 1.1 EV. Oh, what do we do? Oh, that's a I'm stupid. Forgive me. I was using Microsoft Edge for this. I don't really know why, but I just went with it. I don't know. I'm not a stickler about it. Um, but yeah, this whole magnitude thing is killing me. But this is why waveforms get distorted. Like, there's no doubt about that. And there's no doubt that this is what temperature does. Now, the ratio and like the rate of change of it might be weird, but it's still like the relationships are the way they are in real life. So it's cool nonetheless. But I wouldn't trust it to actually predict what a transistor will do. Nope.